Okay, I would like to show how to determine the potential from the electric field. I'm going to use this expression that we proved before and the expression for the electric field generated by a single particle. What you have to do, first of all, I'm going to substitute, right, the equation number 2 in the equation number 1. I'm going to explicitly write all these the terms in this equation. So, and this here is minus the integral of this r I to r f of 1 over 4 pi epsilon 0 over 0. This is going to be q squared and this is r at our product with, so this is of course this what I represent here in this displacement here is radial too, going to be r at r. We know that this scalar product here is going to be 1 parallel. So this is going to give me, I can put these constants outside of the integral. This is going to be 4 pi epsilon 0 here minus, almost forgot. Now let's put charge constant 2 outside of the integral and r to minus 2 dr. This is a polynomial, right? You just have to add the minus 2 1, the denominator of the minus 2 1, there's going to be minus 1. This is going to give me, write this here, this is going to be, and copy actually, copy here so I don't have to write everything again, and lose the line here, minus 1 is going to limits of pi r that's basically is going to give me final expression here. That's very easy. This is integral is very common, right, in calculus 1 I guess for us, so no big deal. If you have any problems just ask me, but going to give 1 and this is going to multiply by 1 are F minus y. Okay, have an expression now. You can work on around this. And like always, like we have been doing all these past lectures, you have to remember we are actually not interested here. You are interested in some asymptotic behavior. That means you want to know when what happens, for example, when this point is very far away. For example, really far away charge, what is going to happen? That means that we are going to take the limit of the first thing that is going to happen is actually that this potential here is going to be zero, right? At the infinity, if you go really far away from the charge, so the potential is going to be zero. Just to remind you guys, I'm analyzing here a point very far away. So first thing that I have actually infinity is going to be zero. It's going to be far away. I'm considering that we don't have any particles in that place. Is zero, and of course I have to calculate the limit here. Mathematically speaking, this corresponds to calculating this limit here. Infinity. And when this happens, we are going to this term here 0 2 I'm going to put in red, so eyes here, and you can easily see that now you have one expression for points that are close to this positive charge u. There is going to be 1 over 4 pi epsilon 0 charge and this distance. Oh, we got like expression for the voltage, for the electric potential. Electric, very good. We can calculate also calculate for can calculate exactly the same for one uniform field. Let's consider the example that we did before, right? Uniform field. Consider like electric uniform electric field. It means that you have electric field generated in a infinite plane, for example. Okay? We have infinite plane here, infinite plane here, different charges, positive and negative, and then you're going to uniform. Remember, this is going to be very, very, very important to understand the capacitor that actually is going to be our next topic. So because this actually models the capacitor, help us understand the physics faster. As you can see, this is going to be easy, right? Since we know that the vector, if you consider reference C right here, x 0, and then my electric field is going in this direction, is going to be E I direction, and we have, I put that delta x here because it's the notation that you have in your book. But if you want to write this vector here, this is also be this ds here that I put in pink. This ds here is going to be this dx. I also has the same in the same direction. So when we do this, here, and this one is 1. That, and then this gives me exactly the expression here that says that the difference in voltage here, or this voltage or potential for a uniform field, just field by the multiply by the, or this case here I'm using this, just the difference, the displacement between the initial and the final points here. So, and this is very, very, very nice because this, first of all, first we have some significance here, guys. Let's put very interesting here. So this is very, very interesting. First of all, wow, this is going to okay, just going on here. So what is the main significance? First one, we can use that to help us understand physics involved in a faster. Start learning next class. Help model capacitor. The second thing is actually this is going to help us find more intuitive units to represent the voltage. Right guys, since look, voltage, electric electric field, because up till now, right, what do you have? Have the actually the electric field in model. Sorry, the units for the electric field actually Newton Coulomb. What is not intuitive and not practical at all, right? When you're problems that involve like volts, new unit, it would be better if you can represent now this in terms of volts. So what do you do? Very easy. You can use this expression here, and we know that the unit of volts, the unit of electrical, not knowing this. Oh, the unit of S. So, from here I can see 1 volt or 1 Newton Coulomb, equivalent of 1 volt per meter. That very interesting. So this is our conversion factor to use instead of using Newton coulombs for the electric field. You can use problems involved to use in this gigantic plastic is terrific, not terrific. Okay, this is the guys, we can generalize this concept, right? I solved here. I found the electric potential for one particle, but if we consider like a system of particles, all you have to do following the what we did before, right? For the electric field and for the electric force, is actually just have to add it up, all particular contributions for all different for different for di- all individual charges in the system. What is going to give us similar expressions that like we used before, like we found before. Just have to sum it up then. And since this is scalar, this is way easier than we did um, the electric field. This is closer to what we did with the electric flux. And if you have like a continuous charge distribution, what you have to do actually just integrate. Is exactly the same like you did before, the same kind of idea. Just have to integrate over the whole object. And again, the main challenge here when you are integrating is actually represent the representation of this one. How I can write this one? This one, remember guys, we have actually, if we have some kind of symmetry, we can represent this as lambda dl. This is the line charge density, then you have surface charge density, and you have volume charge density, another line for V. This is the main challenge actually is here. Describe this and actually and integrate this part here. Okay, like you have been doing before. Remaining. I'm going to do another. I'll try to solve some problems next time. I'm just going to demonstrate for you guys the opposite now, right? We did how to determine the electric potential from the electric field, and now I'm going to show you how to the opposite, how to determine the electric field from the potential, and that's the way easier actually. Remember, we have here the electric field. There is a vector. I'm considering the electric field for the same case like before, right, my friends? I'm using the electric field. Here is going to be E. On 4 pi